Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered why sometimes when you try to learn something new, it feels like your brain is working in two different gears? And they're not quite in sync. Well, a new study dives deep into this, and it turns out our understanding of how our brain learns new movements might be a bit off. Today, we're talking about how our brains learn to adapt to new motor tasks, like reaching for something in a virtual reality game where the controls feel a little wonky at first. Scientists have long thought that our brain uses two main systems for this. One is like a conscious, deliberate learning process, and the other is a more automatic, unconscious one. They've usually assumed these two systems just add up together to create our final movement, but some recent research suggested that this simple adding up might not be happening. The big question driving this study is, are these two learning systems really just adding up, or is something trickier going on under the hood? Think about learning to drive a car with a manual transmission. You've got the explicit strategy, like consciously thinking, okay, I need to press the clutch, shift to first, and then gently release the clutch while giving it some gas. That is your conscious explicit learning. Then there is the implicit recalibration, that is the feeling you get. After a few tries, your foot just knows how much pressure to apply to the clutch without you overthinking it. That is the implicit automatic part. Researchers have pretty much assumed that the total way you learn to drive effectively is just the sum of these two, like a simple equation. Total learning, explicit learning plus implicit learning. And this idea, this additivity assumption, is super important. It is how scientists figure out how much of each type of learning is happening. And it is built into a lot of the computer models that try to understand how our brains learn. But here is where things get interesting. Some recent studies looked at how these two learning processes relate to each other. They used a method called regression, which is basically a way to see if one thing tends to go up or down as another thing goes up or down across different people. They found that the way these implicit and explicit learning measures were related didn't quite fit the simple adding up idea. Specifically, they looked at a thing called a regression slope. If the two systems were perfectly adding up, they expected this slope to be a specific number, kind of like a perfect trade-off. When they saw a slope that was different from this expected number, they said, aha, this means the additivity assumption is violated. They called this subadditivity, meaning they don't add up neatly. Now, that sounds like a big deal, right? If the foundation of how we understand motor learning is wrong, then a lot of past research and current models might need a serious rethink. But this new paper argues that this whole line of reasoning is actually mistaken. The authors say that the people who found these additive slopes were actually misunderstanding what a regression slope tells us. They call it a category error, which is a fancy way of saying they were mixing up two different things. So, what is the difference they're talking about? Well, additivity is about how learning processes combine within an individual to produce a behavior. It is about that equation, total learning, explicit learning plus implicit learning. Do these two parts truly sum up to give you the final action? On the other hand, regression slopes tell us about the covariance structure. That's a fancy term for how two things relate to each other across a group of individuals. Do people who show a lot of explicit learning also tend to show a lot of implicit learning, or maybe less of it? These are two very different questions. The authors here did some clever mathematical work and running simulations to prove their point. Let's dive into that. If we assume that total adaptation, A, is indeed the sum of implicit I and explicit E learning, so AI plus E, and we're measuring A and E to figure out I using subtractive logic IA. What does the regression slope between I and E really look like? What they found is that the slope isn't automatically -1, which is what you would expect if there was a perfect trade-off required. Instead, the slope actually depends on how total adaptation, A, is related, or covaries, with the measured component, say explicit learning E. If total adaptation varies a lot from person to person, and that variation is related to how much explicit learning they do, then the slope between implicit and explicit learning won't be -1. To show this visually, imagine a graph. If everyone in the study learned the exact same amount, then any difference in explicit learning must be balanced by the implicit learning, forcing that perfect -1 slope. But in real life, people adapt differently. Some learn a lot, some learn a little. This variation in total adaptation is key. If people who learn a lot tend to use more explicit strategies, that creates a positive link between A and E. This link, according to their math, directly influences the slope between I and E. So the fact that the slopes are off from -1 doesn't mean the systems aren't adding up. It just means that across different people, the amount of total learning is related to how much explicit or implicit learning they used. They ran computer simulations to test this, feeding them data that followed their additive model, AI plus E, but with different levels of correlation between total adaptation and the measured components. What they found was exactly what their math predicted. The regression slopes changed a lot depending on these correlations, and the -1 benchmark was often rejected, not because additivity failed, but because the simulated people showed these realistic patterns of individual differences. They even point out that the slopes reported in actual studies, which are often somewhere between -0.1 and -0.6, fall well within the range predicted by these simulations, even when additivity is true by construction. Even more interestingly, they show that these sub-additive slopes are actually predicted by other models that do assume additivity, but propose that the implicit and explicit systems compete to learn from the available error or feedback. In these competition models, if you use a lot of explicit strategy to correct a mistake, there is less error left over for the implicit system to learn from. This naturally creates a negative relationship between how much explicit strategy you use and how much implicit learning you do, even though their contributions still add up to the total adaptation. Now, what about when researchers try to measure implicit and explicit learning independently, without using subtractive logic? This seems like a good way to truly test additivity. The authors anticipated this objection. They say that even with independent measures, regression slopes don't test additivity. They show that the expected slope in this case is simply the correlation between implicit and explicit learning, scaled by their relative variances. Additivity, again, only says that I plus EA. It doesn't place any rules on how I and E are correlated. You could have them positively correlated, negatively correlated, or not correlated at all, and still have them add up perfectly. So, a slope that shows a negative relationship between implicit and explicit learning doesn't mean they aren't adding up. It just means that across the individuals studied, those who learn more implicitly tended to learn less explicitly, or vice versa. This is a really crucial point. The studies that reported subadditive slopes were looking at regression relationships. They saw a slope that wasn't -1, and jumped to the conclusion that additivity was broken. But, as this paper explains, regression slopes are about how things relate across a group, not how they combine within an individual. It is like looking at a group of people and seeing that taller people tend to wear larger shoe sizes. That is a correlation. It doesn't mean that height and shoe size are adding up to create something else. It just means they tend to go together. The authors also address other potential objections. For example, some might say the task itself forces a trade-off. If the goal is to counteract the 30-degree rotation, then maybe the explicit and implicit learning must add up to exactly 30 degrees. However, they point out that this isn't what happens in reality. People adapt to different degrees. Some overcompensate, some undercompensate. So, the total adaptation isn't fixed, and that variation breaks the idea of a mandatory trade-off. Another objection is about measurement issues. Different ways of measuring explicit learning, like asking people to report their intentions versus seeing how much they change their movements when they know they can, sometimes give different results. The authors acknowledge this. They say these discrepancies highlight problems with our measurement tools, but don't necessarily mean the underlying processes aren't additive. It is like having two different rulers that give slightly different measurements of the same table. It doesn't mean the table itself is somehow less than a table. They also tackle the idea of loose additivity, where they test if the sum of measured implicit and explicit learning actually predicts total adaptation with a slope of 1. This is a better test, but they argue that measurement noise can still throw off the results. If your measurements of implicit and explicit learning have errors, their sum will also have errors, and this can make the predicted slope look less than 1, even if the system is perfectly additive. So, what is the big takeaway here? The authors argue that the evidence for subaddidity is not evidence against the idea that implicit and explicit learning simply add up to produce our movements. Instead, this evidence points towards how these two systems might interact during the process of learning itself. They might compete for error signals, or compensate for each other's noise. This competition or compensation happens during the acquisition of skill, but their final contributions to the motor output still sum up. Think of it like muscles. You have agonist muscles that pull a joint in one direction and antagonist muscles that pull it back. They are closely coordinated, and if you only look at their individual activity, you might see them working against each other, but their forces still combine at the joint to produce smooth movement. Similarly, implicit and explicit learning systems might be competitively inhibited during learning, meaning they influence each other's update in a way that creates a negative correlation, but their final actions still add up correctly to create the movement. The authors strongly recommend moving away from using regression slopes as a primary way to test additivity. They suggest that more rigorous methods like formal model comparison, where you directly pit additive models against non-additive ones and see which one best predicts new data, would be a better path forward. So, to wrap up, this paper is a crucial reminder that correlation doesn't equal causation. And in this case, correlation doesn't equal non-additivity. The observed negative relationships between implicit and explicit learning are likely a sign of sophisticated coordination during learning, not a breakdown in how our brain's learning systems combine. The assumption that they add up to produce behavior is likely still a solid one. What do I think about this research? I think it's a really important paper that clarifies a significant misunderstanding in the field of motor learning. The authors do a fantastic job of breaking down complex statistical concepts into understandable terms. They've shown that a seemingly strong piece of evidence against a fundamental assumption might have been misinterpreted. It highlights how crucial it is to understand precisely what statistical tools are measuring. Correlation across individuals is a different beast than summation within an individual. The strength of this study lies in its clear mathematical derivation and its use of simulations to demonstrate the abstract concepts. It tackles a direct challenge to a long-standing assumption with rigorous analysis. However, like all research, it is not the final word. While they convincingly argue against the slope test for additivity, definitively proving additivity in complex biological systems is challenging. The paper itself points out the difficulties in perfectly measuring all components and the temporal instability of learning processes. Future research could focus on those more advanced model comparison techniques they suggest, directly pitting additive, competitive, and other interaction models against each other using sophisticated experimental designs. The real-world implication here is that our understanding of how we learn new skills, like sports, musical instruments, or even just adapting to a new tool, is likely still based on this foundational idea of processes adding up. While the way these processes interact during learning might be more complex and competitive than previously thought, the fundamental way they contribute to our final action is probably still a sum. This could mean that interventions aimed at improving motor learning can still be based on principles that assume this additive combination. If you found this breakdown helpful, please give this video a thumbs up. Leave a comment below sharing your thoughts on motor learning. And don't forget to subscribe to RUBIN'S Mind Lab for more explorations into the fascinating world of psychology and neuroscience. Thanks for watching, and I'll see you in the next one.